Hello everybody, WeiEn Physics here, and this is another episode of Physics Speedrun, where I try to finish 20 completely random multiple choice questions under 20 minutes. If you would like to try this yourself, you can pause the video right here and click on the first link in the description below. If at any time I'm going too fast, you can always pause the video, go back to the start of the question, and repeat it as many times as you want. You can also change the video speed by using YouTube's own video settings. So without further ado, let's get to it. So I have my timer here, and I'm going to start my timer right now. Figure 9 shows a manometer. Calculate the pressure of the gas if the atmospheric pressure is 76 cm mercury. So what does this mean? It means that in usual situations, the atmospheric pressure will push the mercury up this column and until you get a 76 cm height of mercury in this column. But now there's only 73 cm. So why is that? It's because this gas itself has a pressure and it's pushing back down. Okay. Either way, I know that this point needs to experience 76 cm mercury's worth of pressure. So in order to get that, I have my 73 cm of actual mercury, and I need another 3 cm of mercury from the gas in order to get 76 cm of mercury worth of pressure. Figure 10 shows a point underneath the water surface of a pond. So determine the depth of the pond. So at the surface of the water, the atmospheric pressure is about 10 meters of water, right? So that's about 10 meters of water pressing down at this point. So you add on this amount of water, you should get 60 meters of water, right, at this point P. So what should be here? It should be 50 meters. Okay. Next one, a coin is put on the base of a pond as shown in figure 13. So in an observation, the location of the coin is at P. What is the refractive index of the water? So because of the refraction of light, things underneath water will look a bit shallower. So we have a formula for refractive index here, which is the real depth. N is equals to the real depth over the apparent depth. Okay, N is the refractive index, and apparent means what does it look like. Okay, so the actual depth, the real depth, is this 4 meters deep. That's the real depth of the coin, and it looks like it is only 3 meters deep. So the apparent is 3 meters. So the N here would be 4 over 3. In an experiment, the velocity of a ray of light in benzene is 1.2 times 10 to the power of 8, and the velocity in vacuum is 3 times 10 to the power of 8 meters per second. What is the refraction index for benzene? Again, this is another formula for refractive index, which is N is equals to C over V, whereby C is the speed of light in vacuum, so that is 3 times 10 to the power of 8, and V is the speed of light in whatever it is. So in this case, in benzene, so 1.2 times 10 to the power of 8. So these two can cancel out. So it's 3 divided by 1.2, that's 2.5. Okay, next one. The table below shows 4 types of material P, Q, R, and S. Each has their own melting point and boiling point. So which of the following is true about the materials in the table above? So number 1, P is liquid at room temperature. Room temperature would be around 25 degrees. So let's look at P. So if it says it's a liquid, so we look at the melting point. So the melting point is at 50 degrees Celsius. That means that anything below that, anything colder than that, it will be a solid. Okay, you have to heat it up to more than 50 or more in order for it to become a liquid. So the first one is wrong. R is gas at room temperature. Again, let's look at the boiling point this time. So the boiling point is 1200 degrees Celsius. That means anything below that, it cannot be a gas, right? So even the melting point is already 800 degrees Celsius. So anything below 800, material R will just remain as a solid. So this is wrong. R is suitable to be used as a heating element, right? Something you use to heat other things up, okay? So definitely, yes, because the melting point and the boiling point are so high. So even when you heat it up to a very, very hot temperature, very, very high temperature, it doesn't melt, okay? So yes, it's very suitable to be a heating element, okay? S appears at a solid at -21. Let's just check the other two. So at -21, that is the melting point. That means the solid starts to become a liquid. Okay, so it can either be a mixture, right, of solid and liquid, or it can also be a liquid at -21 degrees Celsius. And Q appears at a liquid at 50 degrees. So 50 is the boiling point. So there can be a mixture of liquid and gas at 50 degrees. An electric heater with a power of 2000 watts is used to heat a liquid for 5 minutes to convert liquid into gas. Calculate the mass of the liquid. Okay, so this one, we were doing this by using the concept that the heat that comes from a heater, which is PT, the energy that comes from a heater, right, is equals to the heat that is used to convert the liquid to gas. So when you convert liquid to gas, there is no change in temperature. So instead of using MC theta, we use ML. Okay, so P, that's 2000. T, the time has to be in seconds. So 5 minutes times 60 seconds, that's 300 seconds, is equals to M, that's what we're trying to find, and L is 2 times 10 to the power of 7. So M should be 2000 times 300 divided by 2 times 10 to the power of 7. So that's 0.03. Okay, the answer is B. Next, an object of 2 cm height is put 15 cm in front of a convex lens with a focal length of 10 cm. Okay, so for a convex lens, first we need to know that a convex lens, right, looks something like this, is a converging type lens. Okay, so the focal length is a positive number, right, and we can use the lens formula, which is 1 over f is equals to 1 over u plus 1 over v, whereby f is the focal length, u is the object distance, and v is the image distance. Okay, so focal length is 10, right, 1 over 10, and object, what is the object distance? It's put 15 cm, right, 15 cm in front of the lens, so 1 over 15. So we're trying to find v, the image distance. Okay, so I'll bring this over to minus it out. So 1 divided by 10, that is minus 1 divided by 15. So 0.033 is equals to 1 over v, and to get v, all I have to do is take 1 divided by the answer, which is 30. So I get 30 cm. Okay, next, calculate the linear magnification of the lens. So magnification, right, can be either the height of the image height divided by the object height, right, hi over ho, or it can be v divided by u, which is the image distance divided by the object distance. So I will use the second one, which is 30 divided by 15. Okay, so I get a magnification of 2 times. Okay, magnification of 2 times. Okay, next one. Figure 23 shows the image of a candle by using a convex lens. The image distance is 20 cm. Okay, I'm just going to assume that this is the object, yeah, and this is the image. Okay, so what is the linear magnification of the object? So again, like I said, magnification is equals to image divided by object. Okay, whether it's the height or the distance. Okay, so I'm going to take the height, yeah. Okay, so the height of the image, that's 100 cm, divided by the height of the object, 50. So I get a linear magnification of 2. So what is the object distance? Now, since magnification is also equals to v over u, right? Image distance, image distance divided by object distance. So 2 is equals to image distance is 20 cm. So what is u? U will be 20 divided by 2, which is 10. Okay. Next one, which of the following is not true? The momentum of a bowling ball must be larger than the golf ball. Okay, some people might want to think that it is true, but it's not completely true because momentum is mv. Okay, so even though the mass of the bowling ball is much higher than the mass of a golf ball, okay, the velocity of the golf ball could be much higher too. Okay, so it depends on two things. You cannot just say the momentum is larger just because the mass is larger. Okay, so this is definitely not true, right? Dropping a watermelon, I'm just going to check the rest of the answers. Dropping a watermelon on the ground is an example of inelastic collision. The watermelon doesn't bounce back. Yeah. Kinetic energy is not conserved in explosion. Kinetic energy is conserved in an explosion. Momentum is conserved in the motion of a balls in the Newton's cradle. Yep. Okay. So when one side of Newton's, you know what's a Newton cradle? It's the thing that looks like this with different balls. Yeah. Oh, it's in the background. It's in the background. It's in the background. Somewhere. Oh, found it. This thing here. Okay. So when one side of the Newton's cradle hits onto the rest of the balls, the momentum is conserved all the way, and the other side will come out. Okay. The momentum. Next question. The momentum of an arrow is very big because, again, the mass times velocity. So mass of an arrow is small. That doesn't cause a large momentum. It's because of the speed, right? The arrow moves at a very high speed. Okay, C. Next one. The heat absorbed during the process is called ice to water. When ice goes from a solid to water that is a liquid, okay, it is the latent heat of no. That's the characteristics. Okay, the heat absorbed is called the specific heat capacity. Right, the specific heat capacity. No, wait, hang on. Latent heat. Yeah. So it's not specific. Definitely not specific capacity because that is the MC theta. Right, when you change from ice to water, you do not get a temperature change. Okay, so it is a latent heat. I don't know why I confused myself there. So latent heat of fusion. Okay. From solid to liquid. If it goes from liquid to gas, right, like water to steam, that's latent heat of vaporization. When is the substance in the liquid and gas state at the same time? So when there's a liquid and gas mixture, that means there's no change in temperature because it's changing state, right? So we want the part where the temperature remains the same, constant. So a horizontal line, right? And liquid and gas, okay, I'm gonna assume that at this point it's a solid. Okay, when you're here at QR, it is solid and liquid mixture, right? Then the liquid increases in temperature, and at ST you start to get a liquid and gas mixture. Okay, so the answer here is D. Okay, figure 31 shows an air bubble in a glass block of length 15 cm. The refractive index of the glass is 1.5. The apparent distance between P and the bubble is 4 cm. So here and here is 4 cm. If the bubble is observed at Q, what is the apparent distance between Q and the bubble? So if the bubble is looked from here, okay? Alright, so first of all, let's find out where the bubble actually is, right? So when you're standing at P, okay, right, the refractive index N is equals to the real depth divided by the apparent depth. Okay, so refractive index 1.5 is equals to the real depth divided by, it looks to be 4 cm away from P. Okay, so 4. So the real depth is actually 1.5 times 4, that's 6 cm. Okay, so this is what it looks like, but what it really is the bubble is 6 cm away, okay, from P. So if the whole length is 15 cm, that means the bubble is actually 9 cm away. Okay, 9 cm away from Q. So when you are standing at Q, okay, the refractive index now, and okay, is still real divided by apparent, yeah. Okay, this is at Q. I'm going to use another color for Q. Okay, let's say purple, right? So N is equals to real divided by apparent, and N is 1.5. The real depth now from Q, remember you're standing at Q, is 9, and the apparent depth is what we're trying to find. So apparent depth will be 9 divided by 1.5, that's 6 cm. Okay, Alright, monochromatic light moves to a semi-prism block as shown in 3.2. Which of the above is not a pathway of the light? Okay, so which of this is not possible, right? Number one, if you come in here and you go to A, that's possible, okay? Total internal reflection, right? If the critical angle, if this incident angle is more than the critical angle, okay? If this angle, incident angle, is exactly the same as the critical angle, it will refract at 90 degrees. So B is also possible. Okay, so C and D is basically refraction, right? When you go from something that it's dense, okay, to air, which is less dense, right? I'm gonna write this down. This is dense. This is less dense. Okay, the speed of light is gonna increase. Okay, the speed of light is gonna increase. When you increase, you are gonna move away from the normal. Okay, you'll bend away from the normal. So this is your angle here. Okay, so this is the normal. When you come out, you will only go. Oh, sorry, I should use yeah, this one. When you come out here, you should only go away from the angle, away from the normal instead of towards, right? So C is possible, so D is not possible. Okay, D is not possible. Next, a stone with mass of 0.1 kg at temperature 5 degrees Celsius is put into a beaker with 0.5 kg water at temperature 28 degrees Celsius. The final temperature is 25 degrees Celsius. What is the specific heat capacity of the stone? So, a stone, this is very easy, MC theta equals MC theta, right? The heat that comes out from the stone, okay, must be equals to the heat that goes into the water, right? That goes into the water, okay? So, the mass of the stone, that's 0.1. Ignore the birds outside. Okay, 0.1. And the specific heat capacity of the stone, that's what I'm trying to find. The temperature change. So the stone is 5 degrees Celsius. Oh, sorry, my bad. It's not that the heat comes out from the stone. The heat actually goes from the water to the stone. Okay, but the idea is the same. Okay, the heat that comes out must go in. And so the temperature change of the stone from 5 degrees Celsius to a final temperature of 25. So that is a 20 degree change. For the water is 0.5 kg, right? Specific capacity of water, if you don't know, is 4,200. And the temperature change for water from 28 to 25. So that is a 3 degree change, okay? So let's see if we can find C. 0.5 times 4,200 times 3 divided by 20 divided by 0.1. I get 3150. So the answer is C. Figure 3 shows a piston trapping air in a cylinder with uniform cross section. At position K, what the pressure of the trapped air is P, right? What is the pressure of the trapped air in the cylinder when the piston is pushed to the position L? Okay, so this is one of the gas laws, right? Okay, in this case, our temperature, yes, the temperature is kept constant. Okay, so we are only looking at pressure and volume. Okay, so pressure and volume, their relationship goes like this: P1 V1 is equals to P2 V2, and let's say K is 1, right? So the pressure at K, that's P. Okay, the volume at K is 3x plus x, right? The whole thing here is 4x. So 4x, okay, is equals to the pressure at L, which we don't know. Okay, the pressure at L, which we don't know. That's what we're trying to find, right? Okay, we're trying to find PL. Oops, PL. And the volume at L, when you push it down, it's only x. Okay, so bring this x over, I'll get 4p, right? Because x and x can cancel each other out. Okay, so PL is equals to 4p. Okay, so the answer is D. Okay. Oh, last one. Very good. I think I don't have enough time. What's the distance between the student and his image? The student is standing 2 meters away from the mirror, so his image will also be 2 meters away. So the total distance between the two will be 2 plus 2, 4. quick math. If the student moves 3 more meters away from the mirror, what is the distance between the student and his image? So if he moves 3 meters away, now he is 5 meters away. And the image will also be 5 meters away, correct? So now the total distance will be 5 plus 5, which is 10. Okay, and that's done. Woo! Almost ran out of time there. Okay, but 19 minutes and 41 seconds. All right, so yeah, okay, hopefully you guys enjoyed that, right? If you like this kind of videos, remember to give it a like and subscribe to my channel for more physics related content. You can also watch part 1 and part 2 of the physics speedrun where I did the exact same thing. And if you try it yourself, let me know how long did you take in the comments below, right? So that's all for today's episode of Physics Speedrun. I am WeiEn Physics and I'll see you in the next video. Remember, never stop learning.